Now we're going to talk about specific heat. So we're going to talk a little bit about heat, and specifically a term called specific heat. So specific heat is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. The units of specific heat are joules per gram degree Celsius. So how much energy measured in joules does it take to change 1 gram 1 degree Celsius? The specific heat varies a lot from substance to substance. Something like water, for example, has a very high specific heat, so it takes a lot of energy to heat up water, and it releases a lot of energy when it cools off. Something like copper or aluminum has a relatively low specific heat, so it takes less energy to change its temperature. That's why when you have like a metal pan with water on the stove, the metal gets hot. It changes temperature much more quickly than the liquid does. If you had an empty pan and just put it on the stove, it would change temperature very fast, but it takes a lot of energy to actually change the temperature of water. Now there's a formula that this specific heat will go into, and it is Q, which is the amount of heat, equals the mass of the substance, which will be in grams. Heat is in joules. So it's the mass of the substance times that substance's specific heat. And then multiplied by the change in temperature. Now this change in temperature is the final minus the initial, and this temperature needs to be in degrees Celsius or in Kelvin. Since a degree Celsius is the same size as a degree Kelvin, it doesn't matter which scale it's on for the temperature change, but it can't be Fahrenheit. So if you're given a problem with the change in temperature in Fahrenheit, you'd have to convert that temperature from Fahrenheit to Celsius or Kelvin before you started the problem there. All right. So one way you may see a specific heat problem is like what I've written on the board here. What amount of heat, which would be Q, is required to change the temperature of 111 grams of copper, which would be the mass of the copper, from 65 degrees to 95 degrees. Our temperature change is 65 to 95. And you're given the specific heat of copper is 0.382 joules per gram Celsius. So really the trick with any of these problems is just figuring out what you're given and where it goes into the formula. So if the question is asking for heat, they're looking for Q. If it's asking for a mass, they're looking for the M. If it's asking you to calculate a specific heat, it's going to be the CP. Or if it gives you the other things and wants to know a temperature change, you're going to be looking for temperature. It's important to remember a mass cannot be negative and the specific heat is not going to be negative. But the change in temperature could be positive or negative, and so the amount of energy going in or out can be positive or negative. In this case, we're putting energy into the system because we're raising the temperature of this copper. So to solve this problem, we would just say, well, Q is going to equal our mass, which is given here as 111 grams. And we're going to multiply it times our specific heat, which was given to us 0.382 joules per gram degree Celsius. Put that in there a little too soon. And the symbol delta means the change in temperature. So then it's the temperature final, which we went to 95 degrees Celsius, minus the initial temperature, which was 65 degrees Celsius. Right. And so if we look across, our units of grams are going to cancel. We have grams on top, grams on the bottom. We have Celsius on top, Celsius on the bottom. Those are going to cancel. And it's going to leave us with units of joules, which are the correct units for heat. So if we plug that into our calculator, we're going to end up with 1272 1272.06 joules. All right. And so now what we would want to probably do is go and clean up and figure out our significant figures. So here we have 3 significant figures. Here we have 3 significant figures. When we take 95 and subtract 65, we're going to have 2 significant figures. We're going to know what's in the tens space and the ones place. So we have to round this to 2 significant figures. We're going to look at our third digit. It's a 7, so then we add 1 to the preceding number, so 1300 joules. So we have 2 trailing zeros. Those are not significant, and so we correctly have rounded it to 2 significant figures. Now since Q, which is the heat, is positive, or we could say Q is greater than 1, then this is what we would call an endothermic process because we're putting energy into the system. So if your Q is positive, you're putting energy into the system. It's endothermic. So the last problem we saw was what we called an endothermic process, in that we were putting heat into the system, so Q was positive. But if you have something where the temperature is changing from a high number to a low number, or cooling, then your delta T is going to be negative and your Q is going to be negative, and that's an exothermic process, meaning it's giving off energy to the surroundings. Right, so if your temperature is going up, or the delta T is positive, your Q is positive and it's endothermic. If your delta T is negative, then your Q is going to be negative, meaning it's exothermic, it's giving off energy. Because again, the mass and the specific heat are always going to be positive, so the Q is going to be negative if the change in temperature is negative. The Q is going to be positive if the change in temperature is positive. So if we have this kind of problem, how much heat is released when a 10-gram sample of copper cools from 99.9 degrees Celsius to 32.1 degrees Celsius, and we're given a specific heat of copper of 0.382 joules per gram Celsius. So we're looking for Q because we're looking at how much heat. We're given a mass, we're given a specific heat, and we're given the 2 temperatures, so we just have to plug those in. Right, so the Q then is going to equal our mass, which was given as 10.0 grams, times the specific heat of copper, which we were told it was 0.382 joules per gram degree Celsius, and then our change in temperature, which is our final temperature minus our initial temperature. So our final temperature is 32.1 degrees Celsius, and our initial temperature was 99.9 degrees Celsius, and then that is going to give us the amount of energy released, right? And so we can see the temperature is dropping, whatever that is, minus 67.8 degrees Celsius, 67.8. We'll get that eventually there. All right, so what we do is just multiply 10 times 0.382 times a negative 67.8, and we end up with a negative 555.96, and our units are joules. Again, degrees Celsius cancel, grams cancel, and it leaves us with the joules. So Q then is negative because the temperature change is negative, meaning we're giving off energy, which should make sense, right? As something is cooling off, that means it's releasing energy to the surroundings. So it's becoming cooler and the surroundings are becoming warmer. And if we're going to look at our significant figures, we have 3 here, 3 here. We know this we know the tens, the ones, and the tenths. So we have 3 significant figures there. So we're going to round this to 3. We look at our 4th digit, it's a 9, so we add 1 to the preceding number. So we have negative 556 joules. So we've given off that much heat.